So, hello everyone. Hello everyone. The topic of our research is the Golden Gate Bridge. Our motivation is that the Golden Gate Bridge is absolutely a miracle of the bridge engineering. The Golden Gate Bridge was the largest suspension bridge before, and it contributed to the traffic in San Francisco. Every day there are about 112,000 vehicles pass through the Golden Gate Bridge. This heavy traffic causes a large number of load, so it is important to research on the stability behavior of the loading and the Golden Gate Bridge's structure.
Well, there are several objectives. The first one is complete the modeling for the bridge. And the second one is study the deformation at different frequencies. And the last is research the live load and the harmonic response. And several details about the bridge has been shown on the screen. Well, in the 19th century, the American gold rush began. The Golden Gate Channel has kept San Francisco from California, where the city's population has soared. The idea of building a bridge came from this, but due to the bad factors such as geography and climate of the Golden Gate Strait, the construction was extremely difficult, and the bridge was opposed by many parties. Then the Bank of America issued bonds with a collaboration with Joseph Strauss and the workers, designed a bridge that was considered impossible at that time. After completion, the Golden Gate Bridge is one of the largest single-hull suspension bridge in the world, and at the same time, it also has the fourth highest bridge tower in the world, which is a miracle of modern bridge engineering. Then Peter will introduce the methodology.
So let me talk about the methodology of our group. I made a simplified model of the bridge on ANSYS based on the real size of the bridge, which is mentioned before. The bridge is 2,737 meters in length and 27 in width. The model is just composed by 3 cuboids, and I put some holes in it to make it more like the real one. Our group gave up the cables and the other details on the bridge in order to simplify the calculations, which can also help us avoid making mistakes when making the model. So our next step is to do model analysis. Our group put meshes with element size of 10 meters on the model. Because of the bridge size, the whole model looks like kind of dark. You can see in the picture on the right, it is so dark. It is black. And then next page. And then we get the frequency of the bridge, which is on the right of this page. You can see the first picture. This is also the data for our modes, which will be mentioned by Andy in the result part. Also, we use different element sizes of meshes to verify the frequency we get. We choose 6 meters, 8 meters, and 12 meters, and the 10 meters we mentioned before. And here is a chart that I made in Excel, which shows the relationship between the different element size and the minimum frequency of each element size. Then we use the largest minimum frequency of the 4 minus the smallest minimum frequency divided by the minimum frequency. And then we got the error, which is about 0.5289%. which is acceptable because it's just little errors. Next page. So our group also considered the life load of the bridge because in the harmonic response part, we need to calculate the stress on the bridge to make the models. And we get this data from the GoldenGate Bridge Research Library, which is the official site of GoldenGate Bridge. We use the life load on the bridge divided by the area of the bridge, which is the length times the width of the bridge. We get that the stress on the bridge is about 222.22 Pascal. For the frequency part, we choose a range which is a little bit larger, but include the frequency range we got. And the frequency is about 0.01 Hertz to 0.08 Hertz. And then we choose the damping ratio of 0.02. And then Andy will talk about result and discussions.
So there are totally 6 modes of the bridge model, and the first mode and the second mode are pretty similar. The deformation are both appearing in the middle part of the bridge. As you can see, here is a video of the mode 1. So it is and this is a video about the mode 2, and as you can see, the mode 1 has a vertical deformation in the middle part, and the maximum coefficient of deformation is 3.1247 times 10 to the negative 5th. And for the mode 2, there are both horizontal and vertical deformation of the bridge, and the frequency is 0.06281 Hertz, and the maximum coefficient of deformation is 2.948 times 10 to the negative 5th. And then for our third mode, the frequency is 0.07218 Hertz, and here is the video. So at this time, the whole bridge deforms, and the maximum deformation point appears as both ends parts of the bridge. The middle part and the middle part has the maximum deformation point, and the maximum coefficient is 2.3566 times 10 to the negative 5th. For the mode 4, the coefficient is 0.077068 Hertz, and at this time, the deformation appears at both ends of the bridge. Here's the video. As you can see, that only the 2 ends of the bridge deforms, and the maximum deformation appears as the middle part of the end bridge. The maximum coefficient is 3.1756 times 10 to the negative 5th. Now for our 5th mode, the frequency becomes 0.07976 Hertz, and here's a video. This one is similar to our 4th mode. The whole bridge deforms, but the maximum deformation appears in the middle part of the bridge. And the maximum coefficient is 2.5849 times 10 to the negative 7th. Then for our sixth mode, the frequency is 0.14591 Hertz. At this time, the tower between the bridge and the between the bridges also deformates. And here is a video. And as you can see, at this time, the maximum deformation appears at the top of the tower, and the maximum coefficient is 4.1926 times 10 to the negative 5th. So after analyze these 6 modes, we're going to analyze research the harmonic response. So here is a graph of the frequency and amplitude. As you can see, the maximum amplitude appears between the frequency of 0.025 Hertz to the 0.03 Hertz. And it is and the minimum amplitude appears between 0.5 Hertz and 0.6 Hertz. So after that, we can find the coefficient stress. So on the picture of the right, we find that the frequency is 0.0268 Hertz, and this frequency is in the domain of our maximum amplitude, and the swipe is negative 56.649 degree. And then when we enlarge the picture, we find that the maximum stress is as a joint part between the tower and the root. And the maximum coefficient is 1.5487 times 10 to the negative 7th. And this means that when the frequency is in the domain of maximum amplitude, we should be focused on the stability of the joint part because the equivalent stress is the largest. And Elvis will give you a summary and conclusion.
Our research analyzed the stability of the GoldenGate Bridge by doing a finite element analysis on it. Mesh analysis was adopted and the 6 modes of bridge deformation were analyzed by building a simplified model. Also, the harmonic response model was made based on the live load, frequency, and the damping ratio. Mode 1 and Mode 2 showed the deformation in different frequencies. Mode 1 showed that the deformation mainly appeared in the middle part of the bridge and the center of it showed the maximum deformation. Mode 2 showed the maximum deformation part moving towards the right part of the bridge. Mode 3 showed the total deformation. The whole bridge had a vibration and each tower between the 2 parts also had light deformation. Mode 4 and 5 showed that the whole bridge has deformations and the maximum deformations appear in the middle of part 1 and part 3 of the bridge. Mode 6 showed that the 2 towers and part 2 have deformations and the tower between part 2 and part 3 has the maximum deformation. In addition, according to the harmonic response, the maximum amplitude is 0.66 meter when the frequency is between 0.025 Hertz and 0.03 Hertz. The frequency of the equivalent stress model is 0.0 to 6 Hz, which is between the domain of maximum amplitude. Moreover, the external load is the most destructive to the joints of the bridge when the frequency is 0.026 Hz. That's it.
So I think that's all of our presentation. Thank you.
Okay, any questions from the students and from the TA?
I think that I have a question.
Good, I want to hear student questions.
I think that you guys things did not model the cable from the tower to the bridge itself, and I think that the amplitude that your results show is maybe 0.6 about 0.6 meters. So have you compared your result to the real vibration amplitude?
Can you please repeat your question?
Oh yeah, I mean that I see that your result of the vibration amplitude is about 0.6 meters, and I'm wondering have you compared this result to the real vibration amplitude of the Golden Gate Bridge?
Actually, we only focus on the damping ratio of 0.02, and then we find an equivalent model, and the and the domain of the frequency is between, as I presented, the domain is between the 0.25, 0.025 Hertz and 0.273 Hertz. So we only focus on the conditions, this condition. So we didn't compare with other amplitude.
Okay, I think I got it. Thank you.
Okay, so I want to clarify something once again, because I think I already made this point last time, if not yesterday, 2 days ago, that when you do this vibration or harmonic analysis, the amplitude that ANSYS is providing you is actually meaningless. You expect to get multiple solutions because this is an eigenvalue. In mathematics, it's called an eigenvalue analysis. It tries to figure out the fundamental modes of vibration of the structure as well as the mode shape. But whatever amplitude ANSYS is reporting in the calculation is actually meaningless. It is only normalization that it is reporting any amplitude at all. What is meaningful in ANSYS simulations are the frequencies and the mode shapes. You are just interested in the mode shapes, but you will never get an amplitude because you have multiple solutions. Okay, the equation that it is solving is AX equals 0. The right-hand side is 0. So what it does is it sets the determinant of A equal to 0. So it figures out the non-trivial solution. And in the process, you're not able to really get the value of X. You just normalize it. So that's what ANSYS is doing. Now, as I've said, the important thing to compare are the frequencies. And I was just interested to know if the group has compared the frequency of their model with the frequency measured or calculated for the bridge. Because I have data for the bridge. All you need to do is to Google frequency, vibration, Golden Gate Bridge, and you will find out the fundamental frequency of vibration of the bridge. I'll show you what I got. Okay, this one right here is what I got from Googling just a couple minutes ago during the presentation. The natural frequency of Golden Gate Bridge is 0.055 hertz. Hertz means cycle per second. If you invert the frequency, you get the natural period in seconds. And you know what period is? You know, if it vibrates up and down like this, one cycle is one period. And I didn't realize that the period for the Golden Gate Bridge is actually very long. See, 18 seconds. It takes 18 seconds for one cycle of vibration to complete. Now, what was reported in this group was a natural frequency of 0.027. And if you take the reciprocal of that, it is 37 seconds, which means to say more than half a minute it takes for one cycle of vibration. I didn't realize it was that long. So I think you overshot the period or underestimated the frequency of the bridge. 0.027 as opposed to 0.055. But even then, it's not an order of magnitude. So to me, that number is quite impressive, you know, because I don't know whether you calibrated the model so that the frequencies are obtained for the real structure.
I think the difference between these two values is because we ignore the cables. This is a simplified model of the Golden Gate Bridge. Yeah, I think in this case the structure is absolutely different, right? So it will cause a different frequency of the natural frequency.
Yeah. Yeah, the comment is made to express my amazement that you were not too far off from the natural frequency. You overshot the period by a factor of 2. You didn't overestimate it by a factor of 10. You are in that range. So my question is, did you refer your frequency or did you calibrate your model so that the frequencies of the real structure are captured approximately by your model? Or you just, you know, got really lucky that you were so close?
Actually, we just build a model on ISS and collect the data.
Okay, so I think that answer means that you just got lucky. That you were so close. Factor of 2 is not too bad if you're really getting all those numbers from nowhere. Any other questions from the students, from the TAs? Any question from Zhu Shuang or from Lei Xing?
Actually, I have a question.
Okay, Raykan.
Yeah. What's the boundary condition for your structure?
Yeah, for the boundary condition, we didn't use it, actually, to be honest.
You have to fix the bottom, right? You have to fix the foundation.
You mean the fixed end of the model?
Yeah, the foot, the feet, the foundation of the piers. You have to fix it at the base, right?
Yeah, I think Peter did it. It's the fixed end of our bridge.
Okay, so and how about the front and back of the bridge? Like it seems these two tips are fixed.
Yeah, it seems to me that the foundations were fixed. The ramps, the approaches, the two ends, are they fixed also? We can figure it out from seeing the vibration mode shape. You
Yeah,
can see from the mode shape.
And I think it's also acceptable to set up a boundary condition for the top of tower to act as a functionality of your cables in your simplified model by just a proposal. I'm not sure.
Hmm.
Okay, so any other question?
I wanted just to ask, like, because the model didn't use the cable, if there was like actually a cable, would it change the modes a lot, and would it be like reducing the stress or?
I think if there are cables, it will reduce the stress because there are some loads that tension in load tension. There are some tensions in cables which will reduce the loads on the bridge, I think. So it may affect the model.
You know, the reason why last year's groups, there were two groups that modeled suspension bridges, not the GoldenGate, but very similar suspension bridges. The difficulty they had with having the cables was, first of all, attaching the cables to the floor of the structure. That's one thing. The other thing is when you do a vibration analysis, the response of the structure is different when the cable is being stretched than when the cable is being compressed. Because if the cable is being compressed, there will be no resistance from the cable because the cable will just buck out. But if the cable is being stretched, it can exert a strong resistance. So that makes the vibration analysis for a cabled state, a structure, a bit more complicated. And that's the reason why they did not pursue the attachments of the cable last year and also this year. But that's a very good point. The cables will have some influence. It's just not trivial to calculate how much their influence will be. Any other question related to this? So if there are no more questions, what I'm gonna do is